Welcome back. Today we're doing more than just solving a problem. We're basically cracking a code. We are diving deep into a single, really cleverly designed question from a linear algebra exam. And this thing, it's not about memorizing formulas. It's built to test if you really get the concepts.
All right, so here's our game plan. First, we'll lay out the challenge. Then, we're going to play detective and interrogate 3 different claims one by one. We'll look at the evidence, test some theories, and at the end, we'll deliver the final verdict.
So here's the setup. It all boils down to one multiple-choice question about a square matrix, we'll call it A. Our mission, should we choose to accept it, is to figure out which of the 3 statements about this matrix is the one, the only one, that's actually true.
And this is it. This is the question that frames our whole investigation. It's simple, it's direct, and it's asking for precision. Is one of these claims true? Or, and this is what we've got to find out, are they all just clever traps designed to mislead us? Let's dig in.
Okay, let's bring in our first suspect. Claim A. This one tries to build a bridge between the fundamental spaces of a matrix, its row space and its column space, and a really important property of its structure, symmetry.
Now, at first glance, this kind of feels right, doesn't it? I mean, if the space built by the rows is the exact same as the space built by the columns, it just feels like there has to be some kind of perfect balance, like symmetry. But this is math. And in math, our gut feeling isn't proof. We need to prove it or find just one single counterexample to bring the whole idea crashing down. So, just to make sure we're all on the same page, let's do a quick recap. The row and column spaces are basically all the places you can get to by stretching and adding the matrices vectors. And a symmetric matrix, that's just one you can flip along its main diagonal and it looks exactly the same.
This is the heart of it. Is this connection an absolute mathematical law? Or can we find some rogue matrix out there that follows the first part of the rule, it has equal spaces, but totally breaks the second part? Remember, just one counterexample is all we need to prove the claim is false.
Okay, let's bring in our test subject. A simple, unassuming 2x2 matrix. We're going to put this little guy under the microscope and see if it breaks our claim.
All right, let's break down the evidence. Look at the rows 1, 1, and 0, 1. They point in different directions, so they're linearly independent. That means they can span the entire 2D plane. So the row space is R squared. Now the columns. 1, 0, and 1, 1. Hey, same story. Also linearly independent. So the column space is also R squared. So yes, the spaces are equal. But now for the big question. Look at the matrix. If we flip it on the diagonal, the 1 in the top right and the 0 in the bottom left, they don't match. It is not symmetric.
And there we have it. We found our counterexample. The if part was true, the spaces were totally equal, but the then part was false, and that means the entire statement is false. Claim A is officially busted.
All right, on to suspect number 2, claim B. This one gets into 2 of the biggest ideas in all of linear algebra, linear independence and invertibility. And trust me, this one has a very, very sneaky trap hidden inside.
You got to read this one carefully. The devil is in the details, right? It says any 2 columns. The claim is trying to sell us on the idea that if you can pick any pair of columns and they're independent, then the whole matrix has to be invertible. So let's see if that logic actually holds up.
And this slide just nails the trap perfectly. For a matrix to be invertible, the entire set of all its columns has to be linearly independent. What the claim gives us is just pairwise independence. Is that the same thing? I don't think so.
Okay, let's put this to the test with a 3x3 matrix. Go ahead, pick any 2 columns. Column 1 and 2? Yep, they're independent. How about column 1 and 3? Also independent. Column 2 and 3? You guessed it, independent. So this matrix totally satisfies the if part of our claim.
But, and this is the big but, here's the catch. While every pair is independent, look closely at column 3. It's just column 1 plus column 2. That means the entire set of 3 columns is linearly dependent. They're all stuck living on the same 2D plane instead of spanning a full 3D space.
And a matrix with linearly dependent columns is singular. That's just a fancy way of saying it's not invertible. Its determinant is 0. So, once again, we found a perfect example where the premise is true but the conclusion is false. Claim B is also busted.
All right, it's time for our final suspect, claim C. Now this one, it looks a little more intimidating. It's got a polynomial made of matrices. But don't worry, we're going to use a really simple but really powerful technique to see if this one holds water. So here's the statement. It's another one of those if-then deals. It claims that if this specific combination, a squared minus a plus 2 times the identity matrix, if that thing is invertible, then a cubed has to be invertible too. Okay, the best way to test an abstract claim like this, pick the simplest, most boring case you can possibly imagine. So let's just say A is the 0 matrix. Now we plug that into the formula for B. 0 squared minus 0 plus 2 times the identity matrix, that just leaves us with 2i. So, step 4. Is B invertible? You bet it is, so the if part of our claim is true. But what about the then part? Step 5. Is A cubed invertible? Well, A cubed is just the 0 matrix again, and the 0 matrix is basically the poster child for non-invertible matrices. So that's a big no.
And would you look at that? We found a matrix A where B is invertible, but A cubed is not. That one single counterexample is enough to prove the entire implication is false. We've investigated 3 claims, and all 3 have crumbled. So, after putting all 3 of these claims under the microscope, we've systematically taken them apart. We've proven that Claim A, Claim B, and Claim C are all false. And that leaves us with only one possible conclusion for our original question.
So, after all that work, the grand total number of true statements is a big, round 0. None of them were true, which means the correct option on that multiple choice test was D, none of the above.
You see, this wasn't just about getting the right letter. It was about understanding why the wrong answers are wrong. We learned that our intuition about spaces can sometimes lead us astray. We learned that any pair is not the same as the whole set. And we really hammered home that powerful logical tool. To kill an if-then statement, you just need one counterexample. And to wrap this all up, I'll leave you with this to chew on. We proved all these statements are false, but how could we fix them? What extra condition could you add to Claim A to actually guarantee symmetry? How would you rephrase Claim B to make it correct? Pondering questions like that, that's how you go from just solving problems to truly mastering the concepts. Thanks for joining the investigation.